In this module we will talk about interference and diffraction of light. The behavior of interference of light behaves similarly with sound, which we will discuss here. Different wavelengths of light colors that are observed on a soapy bubble is due to the interference of light. The interference is due to the thickness of the surface of the bubble where light reflects at the surface and interior surface as shown here. Interference is the addition of two or more waves. Shown here is a monochromatic light hitting a double slit which creates two wave points and creates an interference pattern. On the other side are two sinusoidal waves A and B. The waves are slightly different, and when we sum these waves we see it in wave C. There are two types of interference. Constructive interference refers to the reinforcement or the addition of the amplitudes of the acoherent waves that arrive at a point in phase. Destructive interference, the cancellation or partial cancellation of the individual wave from two sources in phase. You see on the figure how the sum of these types of waves look like. For constructive we see that the amplitude has increased, and for destructive it has flatlined for waves that are mirror images of each other. Let us recall some physical quantities of waves represented by this cosine function. We see the graphical representation of the displacement x, a function of cosine. We know that one complete cycle is one rotation, and here we see it in a wave form. One complete cycle or one period simply starts and ends at the same point. We can also do this for a sine wave. Similarly, we have the graphical representation of a wave but as a sine function. We see the graphical representation of the displacement x, a function of sine waves. And in phase and out of phase simply refers to the difference of the position of the waves. Here we see that it refers to phase difference. So when we say it is in phase, that means that the phase difference is equal to 0. This suggests that they are identical waves and moving at the same position all the time, which will give a maximum amplitude when they are summed together. When the waves are out of phase, it means that the phase difference is half a cycle. Half a cycle would result in a wave that is an inverse image of the wave, and the sum would result if the waves is a flat line, since they will cancel each other at each point. We can also consider the term of wavelengths, and when we say that they are out of phase, we can express it as the waves have a 1/2 cycle wave difference. Here we examine some conversions of the phases. Wave cycle of 0 is expressed as 0 radians or 0 degrees. Applying the sine function gives a 0 value. So when we say it has a 1/2 wave cycle, it refers to a pi radians value or 180 degrees. The figure below relates the degree positions with sine function. So we see that it is at a maximum when it is at positions 90 and 270 degrees, and at minimum at 0, 180, and 360 degrees. So this means that the phase difference of 0 wave cycle refers to 0 degrees, and 1/2 wave cycle means 180 degrees. 1/2 cycle simply means that one of the waves is advanced by half a cycle or 180 degrees. Here we have two source points S1 and S2 waves. As they intersect at point P, constructive or destructive type of interference is formed depending on the difference of their wavelengths. For constructive interference they must be in phase at point P. For destructive interference to occur at point P they must be out of phase by a half. Note that the factors are expressions of cycles, such that in the destructive interference the 1 has refers to 1/2 cycle or half of the wavelength. Here we have a sample problem on double slits. Two coherent waves interfere at an observation point 161 meters from one source and 295 meters from the other source. What is the wavelength that will give constructive interference? We draw the problem and use equation 1 to determine at the point of the observer a constructive interference from these two sources. Here we consider the first order constructive interference, or m equals to 1, not m equals to 0. For m equal to 0 would result in a distance of 0, which would not make sense if they are positioned r greater than 0. So for m equals to 1 we have the wavelength as the difference of the distances of the two sources. The wavelength that will give constructive interference has a length equal to the path length difference, which is 134 meters. An incident ray as a pulse wave as shown by the bottom wave. A general behavior of light waves is that it is reflected with a 180 degrees of phase change when it travels from a low index of refraction material it is initially traveling and hitting a material of higher index of refraction. For interference of light in films we examine some general rules. The behavior of in-phase and out-of-phase interference in films is summarized here. A wave traveling from a lower index of refraction to a higher index of refraction undergoes 180 degrees phase change. We see that wave 1 appears to have that condition for its reflection. No phase changes when it travels from a higher index of refraction to a lower index of refraction, as we see the reflection on the inside surface where its index of refraction NB is greater than NA. The wavelength of light traveling inside the medium lambda n can be expressed as the wavelength of light in vacuum as shown in equation 3. Let us examine a bit more on the behavior of light as pulses. So for the ray 1, we see that when we send an incident pulse we see that when it is reflected it becomes inverted by 180 degrees or half a cycle. For its refracted ray it remains in phase but with lesser amplitude. For ray 2 it is the refracted light from the inside of the medium having a higher index of refraction. Examining further rays 1 and 2. Ray 1 is reflected with 180 degrees phase change, and in terms of the wavelength it can be expressed as equation 4. This is half of the wavelength n since it is out of phase. Ray 2 is refracted with no phase change but it travels inside the medium with a length that is approximately equal to 2t or twice the thickness. The relationship of ray 1 and ray 2 can be expressed as equation 5. We note that the incident rays are oriented approximately perpendicular to the medium surface. So the angles theta 1 and theta 2 are close to 0. When the condition of rays 1 and 2 are equal to the equation here, then they are in phase when they recombine. So that means the conditions for constructive interference for films is given by equation 5. Substituting equation 3 to equation 6 we get equation 7 for constructive interference in terms of the wavelength of light in a vacuum. N here refers to the index of refraction. To determine the destructive interference formulation for thin films we simply reduce it to the equation 8. This appears to be opposite with our previous understanding of constructive and destructive interference, but this formulation equation 7 and 8 applies to thin films. As light travels in a medium it is affected, and we recall the equation for light. So when light travels a denser material its speed decreases. Here we have a sample problem on interference on films. Calculate the minimum thickness of a soap bubble film that results in a constructive interference in the reflected light if the film is illuminated with a light with a wavelength in a vacuum with wavelength of 600 nanometers. The thickness for a constructive wave is given by equation 5. We recall the equation for the wavelength as it moves inside a medium of index of refraction. Substituting this equation to equation 1, we get the value of the thickness of the soap bubble film, which is about 112 nanometers. In this case we determine if there will be a constructive interference if the thickness of the soap bubble film is doubled. Doubling the thickness, we simply multiply it by 2. To determine if it has constructive interference, we determine the value of T for m equals 0 and 1. We see that for m equals to 0 is equivalent to the thickness T, and for m equals 1 we see that the thickness using equation 6 is about 338.3 nanometers. Since 225 nanometers is not equal to the value of T for m equal to 0 or 1, therefore there will not be constructive interference when doubling the thickness of the soap bubble film. Here we have a sample problem on light traveling to more than one media. Solar cell devices that generate electricity when exposed to sunlight are often coated with a transparent thin glass of silicon monoxide with index of refraction equal to 1.45 to minimize reflective losses from the surface. Suppose that a silicon solar cell with index of refraction n equals to 3.5 is coated with this thin film of silicon monoxide. Determine the minimum film thickness that produces the least reflection at a wavelength of lambda equal to 550 nanometer near the center of the visible spectrum. Compared with the figure, rays 1 and 2 have a phase shift of 180 degrees. Ray 1 has phase shift since the wave moves from a lower index of refraction to higher index of refraction, or the ray 1 moves from air to silicon dioxide. Ray 2 has phase shift since it moves again from high to low index of refraction, or ray 2 moves from silicon dioxide to silicon. The thickness is then determined by using the equation here, and we get that the thickness of the silicon dioxide is about 94.8 nanometer. Newton's rings exhibit interference of waves on a plano-convex lens on top of a flat glass medium. We see that there is an air gap which we call a thin film of air between the curved glass and flat glass with varying length. The length of the thin film of air starts from 0 at point of contact to a thickness T as shown in the figure. We see that this thickness of thin film of air T varies with the radius r as it moves outward. An incident wave hits the surface of the plano-convex lens and transmits inside it, then it reflects on the curved surface. This wave moves from a material of higher index to a boundary with a lower index, thus it reflects with no phase change, wave 1. See yellow dashed circles. The second wave is the one that is transmitted from the curved, and it reflects on the air gap where it hits a material with higher index of refraction, thus it reflects with phase change, wave 2. See green dashed circles. The constructive interference condition is given by equation 7, and the condition for the destructive interference is given by equation 8. The air gap between the curved glass and flat glass is the thin film of air, so the index of refraction that is mentioned in equations 7 and 8 is for air. Comparing the figure of the light and dark fringes, we see that at the middle of the curved lens it has a dark spot, which suggests that at the contact point O it has a destructive interference, thus no phase difference. Calculating the rings of constructive interference, bright ring, and destructive interference, dark rings. The dark spot at the middle or contact point O indicates the destructive interference. The radius r is determined by examining the right angle as shown by the equation here. The distance t square is so small compared to 2tr, so we can approximate it to r square equal to 2tr. We recognize that the length 2t is the path difference of waves 1 and 2, so the value of 2t is given by equation 10. Equating 10 to the conditions for constructive and destructive interference, we have equation 11 and 12. They are obtained by rewriting it based on the conditions for the type of interference. So for constructive purposes we have equation 11. For destructive we have equation 12. At the origin point or contact point we see that it has a dark spot and is positioned at a distance r or radius equal to 0. And this distance happens only when it is destructive as shown here. Here we have a monochromatic laser source sending a consistent series of pulses. In front of the laser is a single slit barrier where light can only pass through the slit. We see that the monochromatic light becomes circular in geometry when it comes out the slit. As we see in the screen on the right, the brightest part is directly in front of the slit and spreads out. Looking at the intensity we see that it appears like a bump that looks like a symmetrical hill, and this is called a Gaussian curve. Here we have a double slit experiment. Again we have a monochromatic laser source sending a consistent series of pulses. In front of the laser is a double slit barrier where light can only pass through these slits. We see that the monochromatic light becomes two circular waves that intersect at various points. As we see in the screen on the right, the brightest part is positioned midway between two slits where there is no slit, and this is due to the constructive interference of these two waves. Two less brighter bars are also observed and they are directly in front of the slits. These bright bars have lower intensity as seen in the graph. Interference in light from two-point sources was demonstrated by Thomas Young. The figure here shows the schematic of the diagram of the demonstration. A plane light waves hits the barrier with slits S1 and S2. These slits become a pair of coherent light sources as they emerge. When examined on the screen we see a series of patterns of light and dark bands. These bands are called fringes. Constructive interference are shown as bright bands and dark ones are destructive interference as they recombine at the screen. Calculating the formulation for the interference. Writing an equation for the difference of the radiuses, we have equation 12. Here we see it forms a right triangle. The difference in the distances will determine if at the intersection will constructively interfere or destructively interfere. Constructive interference, where bright spots occur at positions I equal to 0 or a multiple integer of wavelengths. So the condition for constructive interference where the waves are in phase is given by equation 13. The condition for destructive interference can then be written as equation 14. Let us consider the relationships of L, D, and lambda. The distance between the screen and the slits, we have the length between slits greater than the distances and with wavelength of the light source. The wavelength of light is in the micrometer size, which is in the order of 10 to the power of -6, and you have the distance between slits, which is 10 to the power of -3. We can determine the position of point P as a function here in equation 15. For very small theta we can approximate this function as a sine function shown in equation 16. This would be approximately true if the cosine of theta is very small or close to 0, which results in the cosine of theta equal to 1, then tangent of theta would be equal to the sine of theta. Vertical position Y function for constructive and destructive interference positions. Substituting equation 16 to equation 15 we get equation 17, which is an expression of the point of interference. To find the position of the constructive interference or bright bands we compare equation 17 to equation 13 and we have equation 18. For the destructive interference we compare 17 to equation 14 and we have equation 19. This equation allows us to calculate both the light and dark lines or fringes. Here we have an example. A viewing screen is separated from a double slit source by 1.2 meters. The distance between the slits is 0.03 millimeter. The third brightest ring or second order is 4.5 centimeter from the center line. For letter A, determine the wavelength of the light. For letter B, calculate the distance between the adjacent bright fringes. You can refer to the figure for more details. For letter A, the third brightest ring or second order would be m equals 2 and we use the equation for bright ring or equation 18. After substituting the known values we obtain the value of the wavelength of light which is about 562 nanometer. This value is around a yellow color or yellow-greenish color. For letter B, we calculate the distance between the adjacent bright fringes. We use the same equation but we modify it as a function for the difference of m and m plus 1 to find the distance between adjacent bright waves. After manipulating the equation, arranging them and substituting the known values we arrive at the difference of the vertical distances which is 22.5 centimeter. So from the figure, the bright fringes are shown here. Intensity in interference patterns. Here we see that aside from creating the fringes we also see that the intensity of the fringes vary. It varies in the sense that the fringes that are not in the middle have reduced intensities. In fact, when the fringes are much farther the intensities will be significantly reduced compared to the intensity positioned at the middle. Two slits producing two identical sine waves that have the same frequency and phase difference angle. Here we tackle the intensity at the point P where it is constructive in nature and as an electric field function. The energy of these waves have a maximum amplitude EO and they are expressed as equation 20 and 21. For constructive interference, these waves are in phase or equal to 360 degrees or 2 times pi. For interference we can relate the ratio of the path difference sigma and lambda with the phase difference angle phi and the length or position 2 times pi using equation 22. Rewriting equation 22 and substituting the value of the path difference sigma we get an expression for the phase angle difference phi as shown in equation 23. Now we calculate the total electric field at point P from the waves 1 and 2. This is done by adding their individual energy as a superposition shown in the equation here. Substituting equations 21 and 22 we have equation 24 for the energy at point P. To solve for this we apply the trigonometric identity shown in equation 25. So we simplify equation 24 and become equation 26. Equation 26 shows that the electric field at point P has the same angular frequency as the light waves but we see that the maximum amplitude is now multiplied by a factor of 2 times cosine half of the phase angle difference. Comparing the equation to the position of constructive interference where we see that at points where they are in phase or constructively interfering they will have a maximum of twice times the energy. The intensity at these superposition points is given by the relationship of intensity and square of the energy as shown in equation 27. So we have the intensity of light at position point P given by equation 28. From the formulation of intensity at point P by equation 28, we find the maximum value expression. The intensity as function of the maximum intensity is given by a rewrite of equation 28 where intensity maximum is given by equation 29. For the condition of sine function for one cycle or 2 times pi, its average value is given by the equation here. Mathematical proof is the basis for this average of sine squared value that you can see elsewhere. From this rewritten formulation of intensity at point P shown by equation 28, we find the maximum value expression. Substituting the equation for the phase angle difference in equation 23, we rewrite equation 28 as equation 30. Substituting the approximation of the sine function from equation 17, we rewrite equation 30 and we get equation 31. Constructive interference will produce intensity at maximum if the quantity inside the cosine function is an integer multiple of pi as indicated by equation 31. So, the position Ya for constructive interference must be equal to equation 18, where m is given as values of positive or negative integers. If we graph this, we obtain the image below, where at y equal to 0 it is at a maximum intensity. Here we summarize the three expressions to solve for the intensity as shown in equations 31, 28, and 30. These equations vary depending on the given quantity. Single slit diffraction is different to double slits in the way the intensity varies. Directly opposite to the slit, the light band appears brighter and much more intense compared to the neighboring light bands. The neighboring light bands decrease in intensity rapidly. 85% of the power in the transmitted beam is in the central band, whose width is found to be inversely proportional to the width of the slit. Hence, the smaller the width of the slit, the broader A is the entire diffraction pattern. From the figure, we write an equation for the difference of the radiuses shown in equation 31. The difference in the distances will determine if at the intersection destructively interfere. At point P, a destructive interference occurs, thus we have the waves intersect at this point with a phase shift of 180 degrees or pi or lambda over 2. So rewriting equation 31, we get equation 23, where m starts at plus or minus 1. A note that we add a plus and minus since the dark fringes are present symmetrically, and a factor m for multiple dark fringes. Note that it does not start with m equals 0, since at that point the fringe is a bright fringe. Considering the lengths L and the angle theta, we have equation 33. For very small theta, we can approximate the function, so tangent theta is approximately equal to sine theta shown in equation 34. We then equate the function 32 and 33 to equation 34 and we obtain the vertical position in equation 35. This position is for destructive interference. Here we have a sample problem. You pass a 633 nm laser light through a narrow slit and observe the diffraction pattern on a screen 6 m away. You find the distance on the screen between the first minima outside the center bright fringe is 32 mm. How wide is the slit A? To find the length of the slit, we use equation 35. We rewrite this to solve for the distance as shown here. M here is equal to 1 since we are talking about the first minima. We then substitute the rest of the known values and obtain the value of A, which is about 1.2 times 10 to the power of -4 meters. That is it for now, and I hope you learned something new today. For questions and comments, you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at diyslearningstuff. Note: please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening and see you next module.